In this next video, we're going to introduce the topic here called Gibbs free energy. And previously, we talked about the speed or the rate of a reaction when we talked about kinetics. So if you remember kinetics, this is one way of looking at reactions when we looked at the rate of reaction or the speed. Now we're going to look at a way to determine looking at a reaction thermodynamically. So when we look at the thermo perspective, we consider, will the reaction happen or not? So will the reaction happen? Not so much the speed. And we can do this by figuring out the Gibbs free energy of our system to determine whether or not this reaction will occur. And whether or not we end up with a positive or negative Gibbs, this abbreviated form here, this delta G. If it's positive, we're going to say it's a non-spontaneous reaction, and then we'll see that if it's negative, the reaction will be considered spontaneous in the forward direction. So we will reference some directionality when we talk about this. So this is the equation for Gibbs free energy. And the delta G, of course, stands for Gibbs. And then we have two terms here. So first we have the enthalpy term, which you would be given a value in, say, kilojoules for your enthalpy, whether positive or negative, and you can reference that back to endothermic and exothermic equations where we looked at positive or negative, rather, values for enthalpy. So negative for exothermic, positive for endothermic. So we'll talk about all that when we plug in some values or we just theorize if a reaction will be spontaneous. Then over here on the right, I pointed to the delta S term here. So temperature times entropy. And the same units that we saw before, joules, Kelvin, will be used. So that's why when we multiply by temperature in Kelvin, the Kelvin will cancel out. And we can combine units of energy to find, again, our Gibbs free energy. So when we see a negative delta G, again, that forward reaction specifically will be considered spontaneous. We will know that in the opposite direction, then in the reverse direction, that would be a non-spontaneous process. And then we know if delta G is positive, the spontaneousness will be in the reverse direction. So the reverse reaction, if we have a positive delta G, would be spontaneous. And then there's this other case here that if delta G is equal to 0, the system would be at equilibrium and neither the forward or the reverse process is really happening. So we can look at this graphically here. So we see this reaction where these terms Q and K. So if you recall, Q is our reaction quotient, K is an equilibrium constant here, and we could liken these to if our Q is less than our K, the spontaneous process will be in this forward direction, and then if our reaction quotient is greater than our equilibrium constant, the spontaneous reaction in the reverse direction. So we'll talk about this we talked about this in a previous chapter, rather, and now we can tie this into delta G. So we always know that any spontaneous process carried out at constant temperature and pressure, the free energy will always decrease, and that we can see here as well. So we start at this higher free energy, and then as this process is occurring, it's going lower and lower in energy. And then this would be equilibrium point here, where we're at that lowest point or 0 for our free energy. So let's take a look at this sample exercise here, number 6, and see if we can calculate delta G for reaction in which we're given the enthalpy here of positive 24.6 kilojoules, and then our entropy is down here, 132 joules Kelvin. And we're at 298 K, so at 25 Celsius, but that's already been converted for us here. So we want to know, is the reaction spontaneous? So we're trying to figure out is, do we have a negative delta G overall, right? So that will tell us, if so, then spontaneous. If we have a positive delta G naught, then we're going to say that it's a non-spontaneous reaction under these conditions. So what equation would we use? Well, the equation that we were given above, the delta G equals delta H minus T delta S. And you see me filling in these degree symbols, these knots. That just indicates that we're at standard conditions. So that symbol right there. So these values could be pulled from a table, etc., if we needed them and they were not given. So let's see here. So we have delta H, so we'll plug that in. So we have 24.6 kilojoules minus our temperature, it's 298. Okay, and we need that to cancel out with our entropy value here. And I'm going to convert this to kilojoules. So I just divided that 132 by 1,000, and I get 0.132 kilojoules Kelvin. And the reason that I did that is so we can combine units easily at the end here. So Kelvin will cancel. I'm going to multiply these two terms together, and that gives me 39 point, we'll keep some extra digits here, 336. Now we're in kilojoules. And then that will be subtracted from 24.6 kilojoules, and that will give us our delta G naught. So this will provide us with an answer that is negative 14.7 kilojoules. And yes, indeed, this is a spontaneous reaction because we have a negative delta G. So we'll continue next time with our next video that describes standard free energy changes.